Good morning, everyone. It's good to have you on board. I want to show you a couple options. If you move your mouse a little bit, you'll see that at the very top of the screen, you can mute both the camera and the mic. And I would encourage you, it's background noise sometimes come through, but when you want to speak, just hit the mic and speak up. Way at the top left corner, there's this blue chat thing, and that will open up a chat window, which I might encourage you to do. And then you can follow and you can ask me questions that way if you'd like to. You can also, as you can see from the message on the screen, you can send me a text message if you'd like to. So with that, I guess let's get started. You were taking a look at the beginning lessons 1-1 and maybe 1-2 possibly. Any questions come up that you would like to raise?
Would you be able to maybe run through problem 45 on 1-1?
Okay. So we'll take a look at that.
Thank you.
Sure. Number 45. So first of all, so here we are. Y equals, let's see if I can grab that. Well, maybe not. I know what I have to do. I have to let's see if that does it. And now come back. All right. So anyway, what do we got here? It's x times the square root of x plus 5. Okay. So all right. And so the directions stated, find any intercepts and test for symmetry. All right. So how do we check for intercepts? An intercept would happen when either x equals 0 or y equals 0. So the question is, let's start with y. When would y equal 0? I think you can see it would happen when either x is -5, because that would create a square root of 0 and 0 times whatever. And it would also happen when x equals 0. Okay, so that would be what would happen when, when we have x intercepts. And then when x equals 0, that'll create, so basically we have 3 intercepts. Okay, now what about symmetry? How do you test for symmetry? Well, symmetry, let's see. So symmetry would exist when you replace x with a negative x and you get the same answer for y, that would tell you that we have y-axis symmetry. Is that going to happen in this case? So for example, if we let's say we have x equals 1. Okay, if x equals 1, then we'd have 1 times the square root of 6. the square root of 6. But what if x is negative 1? If x is negative 1, now we have negative 1 times the square root of 4. And that's not the same result. So we don't have y-axis symmetry. On the other side, if y equals 0, you know, so that's how you test for symmetry. So it looks to me like let me think about this. Let's try x equals 4. If x equals 4, then y equals 4 times the square root of 9, which is 3, so that would be 12. And if x equals negative 4, we get y equals negative 4 times the square root of 1, and we don't get the same thing. So it looks like we don't have symmetry either way. And now we could check a graph here. Let me just quick do that. We'll look up Desmos, which is what I'm going to suggest to most of you. And then we can type in our function. And we can see why we didn't have symmetry either way. So as a checking device, you'll see me frequently go to Desmos. So basically no symmetry. And we checked out our intercepts, 0, -5, and 0. Let's just quick check those on the graph. 0, -5, yeah, are our two intercepts. So I should put down the number on that one. What was that, number 45? Other questions that you would have? Okay, well, I'm going to, you can bring up questions anytime you want to. And remember, you can either use the chat window, and you can open that up by going up to the top left, and when you move your mouse, you should see this little window come up on the left, and way at the top left, there's this blue text thing, and that's your chat window. You can type in there. You can certainly text me by using my phone number. Let me just go back and look at that. So there's just a reminder of the options you have. Okay. So the first lesson is called An Introduction to Functions. Yeah, I just thought I'd give a nod historically to two of the guys that have a lot to do with that. Leibniz on the left is one of the co-discoverers of calculus, and on the right is Leonhard Euler. Let's see, I got to move it so we can see that. Oh, and I should remove the windows at the bottom so you can see better. There we go. All right. So, and Euler is especially responsible for function notation. You can see I underlined in red there, y equals f of x, which, I don't know, it may bug some of you, but it turns out to be extremely useful and very useful when it comes to calculus. So we're definitely going to be giving a nod to Leonhard Euler as every time we use function notation. So I don't normally use slides, but here are some slides to get us going. An introduction to functions. So first of all, the difference between a relation and a function. In a relation, I mean, there's nothing special going on. One is linked to the other. A relation, anything fits a relation. But not anything fits a function. And here we have, so for a function, we do have this restriction that when there's a given x in the domain, there can only be one element in the result. So in other words, for a function, you can't have two different results. An example would be, I go to the grocery store and I buy a gallon of milk, and they charge me a certain amount. And then one of you goes and gets a gallon of milk and they charge you something different. We would never stand for that in America, and a function wouldn't stand for that. So for a given x, there can only be one value for y. Yeah, here's a picture that sometimes describes that. You've got a given value of x, there can only be one value of y. So each x points to only one y. So one way you need to be able to recognize this is when given a set of ordered pairs, is it a function or not? And in part A, what makes this a function is we never even have the same x. -2, there are no other x values of -2. So anything goes, it's fine. There's no problem. That's a function. When we get to part B, we have -1, and we have two different answers for -1, which makes it not a function. Yeah, and it just points out here that f is the most common, f of x is the most commonly used term, and that's because f is function. And then sometimes when we need a secondary, we'll go to g, probably because g comes after f. So you're all familiar with that. One of the really useful things about function notation is when we say f at whatever. So like here, in this case right here, we have f at -2. And that just means when -2 is in place of x, then out comes a 9. And this is awesome because when you say f of -2 equals 9, you literally have the ordered pair, -2, comma 9. So very, very useful. And let me undo that. Back to my arrows so I can move this around a little bit. So you can also plug in an expression like f at x plus 2. F of x plus 2 means I literally have to substitute an x plus 2 in place of x. So wherever there was an x, and there was an x in two places in the original up here, I placed in an x plus 2. And then we can actually compute, simplify, and we come up with stuff like this at the bottom. F at x plus 2 is 4 minus x squared. So substitution is incredibly important. We're going to be capitalizing on this function notation when I first show you how to do a derivative. So I make sure I'm not buzzing by everybody. Are there any questions? Okay. So the term domain is all the possible values for x, all of them. So in other words, is there anything I can't plug in for x? In this function, 3x plus 5, there is nothing I can't multiply by 3 and add 5. So therefore, we would say the domain is all real numbers. Now here you can see that's not true. For this function, x, the square root of x minus 3, I can't just plug in anything here, because if I plugged in a 0, for example, for x, this would not compute to an answer that we can make sense out of. Over the real numbers, there is no such thing as a square root of -3. Yes, there are the imaginaries, but over the reals, no. And so we would say the domain is, yeah, 3 is okay, because it's okay to take the square root of 0, but anything other than 3 or bigger is out. So here's how we would state that. The domain is all x such that x is greater than or equal to 3. So I just have another example here. Y equals 3 minus x. F of x equals 3x minus 3. And then what's f of -3? You just literally substitute in for x a -3. 3 times -3 is -9. And -9 minus 3 would be -12. Again, notice, neat notation. F of -3 is -12. That relates to this right here, this ordered pair. When you plug in a -3, out comes a -12. What's f of x plus 1? Plug in plug in an x plus 1. So we do that. Simplify, and you wind up with a 3x. So maybe unusual ordered pair, but this one right here, x plus 1, comma 3x, is literally represents, hey, when you plug in an x plus 1, out comes a 3x. And, I mean, you can even do weird things like f of triangle. Plug in a triangle for x. 3 triangle minus 3. Okay, so we're just trying to hammer away at what's allowed in function notation. So here's one right here. If we want to find the domain of a function, then you've got to ask yourself, is there anything x can't be? Is there anything x can't be? Well, we know we can't have a 0 in the denominator. So your question to yourself is, what would cause x, what would cause the denominator to become 0? And you can probably see there's 2 things that would cause that. X equals 1 or x equals -1 are not, those would not be allowed, because division by 0, sorry, is not a function. It's not something we can do in math. So here we say the domain in a negative way. We say, well, x can't be these 2 things. It could be anything else. And how does that translate on a graph? Probably it comes to an asymptote at those 2 values. Here, let's just take a look at that. So we have x plus 2, x squared minus 1. So we'll go to Desmos. We'll turn that off. And we have x plus 2. Let's put parentheses around that. And then over x squared minus 1. And you can see that at x equals 1, we've got this vertical asymptote here, and x equals -1, we also have a vertical asymptote. So that's frequently what will happen in a domain situation. Okay. So a very important concept we are going to get into is how does one, what's a difference quotient? Okay, so you've got, what it amounts to is what we've got here is two generic points. That one and that one. And we want to find the, you know, what the difference quotient. So this one was just called x, f of x. So that's an ordered pair. Plug in generic x and out comes an f of x. And over here, we're going to move over to the right, h units. And so this is x plus h. And when you plug it in, you get f of x plus h. So we've just literally have two generic points here. Now, what's basically the slope of that line? Well, it's the change in y over the change in x. So we take f of x, the change, what's the difference between the two y's? You take f of x plus h minus the y coordinate of the first point, f of x. And then on the bottom, you put the change in x, x plus h minus x, which is just an h. And this is a difference quotient. And that's huge. As we develop the basis for a derivative, it's all based on finding difference quotients. So here, let's take a function and let's find its difference quotient. So up at the top, f of x equals 2x minus 1. That's our function. Find the difference quotient. So what we need to do is this thing on the bottom here, this, you know, let me just highlight here. It's this thing right here. We need to find that difference quotient that we just figured out, f of x plus h minus f of x all over h. Well, in order to do that, we have to find f of x plus h. So when we do f of x plus h, we have to plug in an x plus h wherever there was an x. So 2 times x plus h. Anyway, that comes out to that. And then we have to subtract the original f of x, it's 2x minus 1, and put that all over h. Well, when you simplify the top, the 2x's go away, the negative 1's go away, and you just get 2h. 2h over h is 2. That's the simplified difference quotient. All right. So this time, let's take one that has, this is, it's a little bit different. It's got a square in it. F of x equals x squared minus 7. So again, I need to find this thing in the top right corner. And before I can do that, I have to figure out what is f of x plus h. So I have to plug in an x plus h in place of x, which I've done here. Remember, when you square x plus h, you don't just get x squared plus h squared. You get those middle terms. You get 2 of that xh. And there's your f of x plus h right there that's underlined. So now I take that, I subtract the original, subtract x squared minus 7, and put that all over h. And when I subtract the x squareds and the minus 7s, I get this thing on top, 2x squared plus h over h. The h is canceled. There is my difference quotient. Okay, those two were still pretty clean, pretty straightforward. And that one we've already done. We've done that one. I see I'm in the wrong place here. Yeah. Okay, let's take a look at this one. So here we have a little bit longer polynomial, f of x equals 2x squared minus 3x plus 2. Find the difference quotient. So, same old deal. We're headed for this box down here, f of x plus h minus f of x all over h. So we got to find f of x plus h. Plug in an x plus h wherever there's an x. And there's two of them up here, so I have to plug it in both places. So first I have x plus h squared times 2 minus 3 times x plus h plus 2. So a bunch of substituting. Finally, you get 2x. You get this line right here. Let me change, I don't know, to something different. I'll change to green. So you get this line right here. 2x squared plus 4xh plus 2h squared minus 3x 3h plus 2. And then a nice, easy way to subtract the original function, f of x, is to literally put it down below the like terms. So negative 2x squared right below. Anyway, so what's left? We get this 4xh plus 2h squared and minus 3h. Minus 3h is left. And that's all over h. And finally, you can cancel, there's an h that you can factor out of the three terms on the top. Canceling gives me this final difference quotient right here at the end. You can interrupt if you'd like. I know some of you, a bunch of you have had this. I don't know if all of you have, but this is really important as we begin our course. All right. Now, let's do this one live. Let me see here. I want to make this a little bit bigger. All right. So, this time we have g of x equals 1 over x squared. All right. And we want to find the difference quotient. So, the first thing we want to note here is that what we're going to be having, what we want to find is g of x plus h minus g of x, the original function, all over h. That's our difference quotient. So that's what we're aiming for. So that means the first thing we're going to want to find is what's g of x plus h. All right. So plug in an x plus h where there's an x. So what's that equal to? 1 over right? So now we've got that. So now I want to take that and I want to subtract the original function, which is 1 over x squared. And then, of course, I have to eventually put that all over h, right? Because I'm trying to, get to that model down there on the bottom. All right, now this creates some difficulties. I need to get, I've got a complex fraction here. I need to get these two denominators to be identical. All right, so let me take my keyboard off here so I have a little bit better room to write. Okay, so I basically have to multiply. In order to get a common denominator, I got to take this first fraction times the denominator times x squared, and this fraction over here times x squared plus 2x plus h. So let's see. So we got 1 over x squared times x squared plus 2xh plus h squared. So that's the new denominator. And then over here, 1 over x squared times, let me move this over a little bit. X squared plus 2xh plus h squared. So all I've done so far is get that common denominator. Now we've got it, right? Except I got to multiply the top by that too. So this top was multiplied by x squared, and this top is multiplied by okay, so running out of space here, I'm going to remove this stuff down here so I have some space. All right. So putting that together, what do I have? Well, I've got the common denominator, so I'm going to copy that down. And on the beginning part, I've got x squared. And on the end here, I've got, you know, this numerator, x squared plus 2xh plus h squared. And of course, that's all over h yet. Okay. So in the top, what happens? X squared minus x squared. So I've got 2xh plus h squared. I'm sorry, those are minuses. So let me get that. So minus 2xh minus h squared. And on the bottom, we've got this same thing. We've got h, but we also, I mean, when you divide by h, that h could go in this denominator. So I've got this times 8 times x squared times x squared plus 2xh plus h squared. Okay, and now we've got it all in one expression. And then you can factor an h out of the top. By the way, are you guys seeing everything on the screen right now, or are your pictures in the way? Somebody speak up, please.
It's good.
Okay, you can see it.
You can hide the pictures next to the microphone mute button if you need to.
Yeah, well, I've got this button on the top that I've already, well, anyway, I'm glad it's good. So anyway, then you can cancel the h's, and finally, we're down to what's left there. And this gets pretty involved when you're dealing with fractions, but that would be the difference quotient. Okay, so we've got that kind of a difference quotient. Yeah, here's one too. I don't know. Let's see. Let's go to the next one. That's another quotient. I wanted to take a square root, so let's go to this one next. Okay. Well, so let's give that a try. All right. So we've got f of x equals x minus 3. And I already stated the domain is limited. As you can see, x can't be below 3. It can be 3, but it can't be anything less than that. So I've stated x has to be greater than or equal to 3. So in your preparation for this, we know we're going to have to find f of x plus h, and we've already got it there. All right, so as we start to write this out, the difference quotient is f of x plus h minus the original function, f of x, all over h. All right, now when you finally get down to your difference quotient, we've got to get rid of this h. Okay, we can't have that left over. So what we're going to do is, what's the technique we can use? We can try to get rid of those roots on the top by multiplying top and bottom by the conjugate of the top. That is x plus h minus 3 plus square root of x minus 3. And of course, we do it on the top. We have to do it on the bottom. Okay, so what's going to happen on the top? What happens when you multiply by conjugates? You get the difference of two squares. You get that first thing squared minus the second thing squared. So that first thing squared is x plus h minus 3 minus the second thing squared. That thing without the root. On the bottom, well, we still have a mess, but that's okay. Just leave it. Okay, so we've still got that. All right, so on the top, what has happened? Well, when you simplify that, the x's go away, the -3's go away, and you wind up with an h on the top. And then the bottom, I'll leave alone. A little bit sloppy here. So that's what you get, and then of course when you cancel, and that is your difference quotient. So we've got the old conjugate method has to be used to simplify.
So you said we had to get the h off the bottom, but there's still an h.
Once you get rid of that h, well, yeah, and this one's okay because see where we're headed is we're going to take the limit of this whole thing as h approaches 0, and as h approaches 0, I can't have a denominator of 0. So the original form here with an h on the bottom was no go. But this h is okay because as h approaches 0, that'll just be, the square root of x minus 3 plus the square root of x minus 3, which is, so, I mean, eventually the derivative as, this is a little early, but you want to take the limit as h approaches 0 is going to be 1 over, because that 0 is okay there because it doesn't create a 0 in the denominator. So, I mean, this is a little early to do this, but when I said the h has to be out of there, I meant that, yeah, we did that when we canceled here. So okay. Does that make any sense?
Yes.
Okay. Yeah, so you're right. I can't just say the h has to be gone. But let's put it this way. The h that would create a 0 in the denominator does have to be gone. So let's see. So let me just check here. Is that from this? I can't remember where this is from. Yeah, I think we're going to wait with that. So let me just see what kind of, where do they ask you to do the difference quotients here? Test for symmetries, intersection, find points of intersection. Okay, next page. Yeah, so I might be a little bit ahead of time here. Yeah, so what I've just gone through is some of the stuff from lesson 1, 2. Yeah, and they eventually get into this definition of slope thing here. And you're getting close to what I was doing. So anyway, I got, I'm maybe a little bit ahead of time, but that's an important, that difference quotient concept is one of the most important things in, excuse me, one of the most important things in calculus. So we're going to be practicing that for a while here. And that's a really big deal. The teacher who teaches shortcuts for derivatives without showing this is getting his students into a lot of trouble for not really knowing what's happening. So anyway, you'll see, we're going to dwell on that a little bit. All right, so at the very end, the core exercises, I don't know, for this time, you probably did the 1-1 things. So you want to start getting into the 1-2 and keep yourself on schedule here. And does anybody have any questions?
Maybe back on the 1-1 assignment, I believe, if you would be willing to go through number 57, I'm sure it's something simple, but I've came up with the same answer every time that's wrong. So
okay, 57. Yep.
Yeah.
Let me go up to the top here. Okay, let's go over here. Okay, so 1 point. So let's change here to the pen. So 1.1, guess we don't need it to be that fat. Number 57. So let me quick look it up. So find the points of intersection. And we've got the two graphs are x plus y equals 8 and 4x minus y equals 7. Okay, so let's go back here. So x plus y equals 8 and 4x minus y equals 7. So, I mean, you've got several things you can do. I personally love to do straight lines, and these are straight because everything is to the first degree. I like to solve for y. So y equals negative x plus 8. And on this one, negative y equals negative 4x plus 7, y equals 4x minus 7. So I would take those two and then let's plot in slope-intercept form. Sorry, actually, let me undo that. And let's insert Let's insert that guy. Okay, and now we can plot those two. So negative x plus 8. So so it's got a slope of -1 and a y-intercept of 8. 1, 2, 3, 4, 5, 6, 7, 8. And it's got a slope of -1. So for every 3 down, 3 to the right. So there's the first one. So that looks like that. And then the other one, 4x minus 7, y-intercept of -1. I'm sorry, -7. 1, 2, 3, 4, 5, 6, 7. And a slope of 4. So for every 8 up, 2 to the right. 1, 2, 3, 4, 5, 6, 7, 8. 2 to the right. Okay. So that one looks like that. The solution is where they intersect. Now I did this with eyeballing, but it looks like the solution is what? 3 comma 1, 2, 3, 4, 5. Now let's go back and let's do the algebra from this. Okay, so let me bring this thing back so we'll just do the algebra. So we have y equals -x plus 8 and y equals 4x minus 7. Since they're both equal to y, we can set them equal to each other. And then we can solve for x, add x to both sides. And add 7 to both sides. And then we can see that x equals 3. And then you can substitute back in to get y. So back up at the top, y equals, if you plug in a 3, so x3, y is 5. And whoops. And that was what we got, remember? 3 comma 5. So that matches up. But you didn't have to do it graphically. I just thought I'd throw that into. I mean, you can do it algebraically like I did at the top. I don't know. Is that clear enough? Did you pick that up?
Yeah, it was just a stupid mistake.
Okay.
Yeah.
Well, yeah, that's how, unfortunately, in math, that's usually what happens, right? Yeah. Anybody else questions? So if you want to move on and work on your 1.2 for next time. Did anybody else have a question? I'm gonna bring the pictures back here. Yeah, did anybody else have a question? Thank you for joining me this morning. I know this was your first chance at all of this, but I think you'll agree, clicking on a link, this is pretty simple. And I'm hoping that this technique will be good for Tuesdays. All right, then we're going to hang it up for today. Thank you very much. I will see you tomorrow.